Glycine is your body's natural blood thinner. That's probably the easiest way to put it. The normal diet gives you 2,000 or 3,000 milligrams a day of glycine, but guess what? It's not enough. I got zero inflammation because I was taking 10 grams a day of glycine. In order to have a heart attack, you probably need to be glycine deficient. It's normal to have minor micro injuries to your arteries, even your coronary arteries, all the time. But if you're glycine deficient, you then get inflammation following from injury. One of the most significant results I've ever seen, just people who have CPS1 deficiency, men don't get heart attacks. The worst processing is cutting the meat off the bone and throwing the bones away. That's the worst kind of meat processing that we do. Glycine is maybe the most or the second most abundant amino acid in the body, but yet most people are deficient in it. I had to pinch myself a few times years ago. When I first made these discoveries, it was like, is this real? Could it be this simple? People to this day still tell me, it can't be that simple.
Hi everyone, we've got an episode all about the link between glycine and heart disease. Keeping our heart healthy, can glycine be a part of it? We have statins, we have surgery, we have blood pressure medications, and heart disease is our number one killer. But Dr. Brand over here, a biochemist who studied immunology and nutrition actually, and glycine extensively, Yale trained, as credible as it comes. And we're going to talk about it. We're going to break it down for you because he believes glycine is a missing piece of this puzzle. And glycine is also something many of us are deficient in because of the way that we're eating today. All the muscle meats, none of the connective tissues and the bones and the other parts of the animal that actually contain the balancing glycine. So welcome to the show, Dr. Brand. I'm really excited to dive in.
Yes, thanks very much. And we eat too much of everything.
Oh, yeah.
We eat too. That also has to do with glycine. Glycine has to do with obesity, with diabetes, and all of those are related to heart disease, as everybody knows. And they're all related to chronic inflammation, as everybody knows. But they seem to not know about how glycine fits in, which fits in so perfectly in that jigsaw puzzle of human physiology and health and disease. And it's somehow it's still not well known. So that's what I'm here for, trying to make it better known.
Yeah, Dr. Brand is on a mission to help people understand that glycine deficiency is a real thing. This is part of a series. So we're breaking down, we've done many extensive conversations. If you haven't seen those, I'll link to them in the description. But we've broken it down to blood sugar and cancer and methylation. And today we're going to talk about the link between heart disease and glycine. So Dr. Brand, tell everyone, how did you get into this work? And why should people trying to prevent heart disease be concerned?
I got into this work because I was with a group that was studying longevity. They were studying aging, and so they were looking at rats and trying to, do whatever they could to their food or whatever to make them live longer. And they came upon something called methionine restriction. That methionine is the great universal methylator, which is an essential amino acid. And if you actually restrict the amount of methionine the animals could eat, by putting a little, they could still eat as much as they wanted, still ad lib feeding, but you restricted the amount that's in their food so that they would just barely have enough to subsist. They were still active and happy and all of that, not neurotic little rats running around, but they didn't grow to normal size. It did inhibit their normal growth, but they lived 30 or 40% longer. Instead of living for 2.5 years, they would live for 4, and stuff like that. That was a big deal. That was back in 1993. They published their first paper. And other groups published. They did it in mice. They did, and so by the early 2000s, it was recognized in the research, the aging research field, as a real thing. Methionine restriction as something distinct from caloric restriction, which you might have heard about, just eating less altogether. So it was different. As a consultant to this foundation, I've been working with them for many years. They said, well, why, can you explain it? So I did some research and I began to look at the literature and realized that, because what I was trying to do then is, what can we feed people that's going to deplete methionine? Can we do something? Because the first thing that occurred to the group was to do a methionine restricted diet. Well, a methionine restricted diet is the most, the awfulest diet you can imagine. Everything that tastes good has methionine in it,
Give us examples. Muscle meat, right?
Muscle meats, yes. Muscle meats, chicken and beef and pork and, bacon and all that stuff is loaded with methionine. Dairy is loaded with methionine. So it's like it would be the strictest kind of a vegan diet. The only thing you might have that's not loaded with methionine for dairy is to have cream in your coffee instead of milk. That'll give you less methionine.
If you restrict methionine, do you also restrict growth?
Yes, well, yes, that's right, absolutely. But this was, longevity was the thing, and so this is what we're looking at animal models, the good kind of animal research, where you take care of the animals, to the techs who take care of the animals. These animals are like pets, the rats and mice, and they look forward to their feedings. They even stick their paws out to have their blood sampled, stuff like that. Oh, sure, because they're pets. What do they know? They don't know the difference between a pet and a work animal or an experimental, subject. If they're treated well, it's like a horse. A horse is a work animal. But could say, "Oh, you're enslaving horses." Excuse me. Everybody works for a living one way or another. It's what you call it, and it's how you treat people that counts. And so you don't treat horses the way you treat people, but you treat them nicely. You treat everything humanely. So it's this kind of animal research I like, and it's very, very useful. So they found that if you feed a methionine-restricted diet, they'd live longer. But why? But why? But why? So doing the research on the methionine cycle, all the biochemistry of methionine, that one which delivers one carbon methyl groups to different molecules like DNA, like neurotransmitters, like hormones, to modify them in ways to make them active or inactive, that sort of thing. Very universal kind of service, molecular service done for the body's overall biochemistry is done by methionine. So in fact, graduate school and even in undergraduate in biochemistry, everybody learns about the methionine cycle, because methionine is an amino acid which is essential. In fact, it's the one you need the least of. Well, why do you need the least of it? It's essential. Because it's essential, your body has many ways of recycling it and regenerating it. That's why 10 to 20% of the population is low methylators. Hey, how come they're not dead? How come you have low methylators in the population at a very high percentage? Because your body has a lot of redundancy and a lot of ways to work around that low methylation. And dietarily, there are other ways we can help work around it so that your physiology becomes really more normal, so that you can go 5 hours from meal to meal instead of desperately needing a snack after an hour or two, that kind of thing. So the reason why a defect in the methionine cycle, which is what these low methylators are, it's an enzyme that helps to recycle methionine. The reason why these things are not fatal defects is because there is a lot of redundancy. And so when you have a lot of methionine in your diet, that methionine cycle that we all learned, how the body concerns this precious little essential amino acid methionine, it ain't so precious. In this society, we have tons of it. We get 10 times more than we need, because the methionine requirements, the daily requirement for methionine is about 300 to 500 milligrams. This is a bulk nutrient. This is an amino acid. So, for example, glycine, the normal diet gives you 2 or 3 grams. 2 or 3,000 milligrams a day of glycine, but guess what? It's not enough. You need 10,000 milligrams, because that's what you need more of, and I can explain why, and I will shortly, but that's how I got into this. And so it was my job to try and find something that would help to get rid of excess methionine. Well, some research had come out in the 1990s about methionine clearance. There's the most abundant enzyme in human liver, at least in America, where we eat so much methionine. The most abundant enzyme in human liver is an enzyme called glycine and methyltransferase. It is the enzyme which is the only initial clearance enzyme for methionine, to get rid of methionine. Glycine and methyltransferase. Glycine means a methyl group is transferred from activated methionine, which is called SAMe. People probably understand that. It's transferred to glycine in order to get rid of that methionine, to get rid of that extra methyl group. And in fact, you need 2 molecules of glycine, one to take that methyl group as glycine and methyltransferase, that's called transmethylation. And the other half of the clearance cycle for methionine is called transsulfuration. And there the glycine is needed in order to make glutathione. I'm not going to talk about glutathione much today, because we could talk for years about that. That's a very big topic. Suffice it to say that making glutathione is one of the 2 ways that every molecule of methionine gets cleared. So you need to waste 2 molecules of glycine to get rid of every excess molecule of methionine, because your liver gets rid of the excess. So you're not doing that methionine cycle an hour after you've eaten that cheeseburger. Your liver is busy getting rid of it as fast as it can.
Right.
So that was my hypothesis then, is let's try and see if we can feed glycine, if that can help to accelerate the clearance of methionine and thereby increase lifespan. So guess what? We did that, published an abstract in San Diego in 2011, and published a paper with the National Institute on Aging with mice in 2018. When it was finally published, I'm not sure. Around there. That was the National Institute on Aging, their interventions testing program, ITP program. And we got the mice, or the rats in my initial study in 2011, they lived longer. They didn't live that much longer. It wasn't as strong as methionine, but they also didn't decrease in size. But importantly, it did not affect the amount of methionine in their blood, not one bit. So an excess of glycine does not help to clear it. There's always enough glycine around. Because remember, glycine, even when you're, that's another thing that's confusing about it. Glycine is maybe the most, or the second most abundant amino acid in the body, but yet most people are deficient in it, because that's not enough. Because glycine has other jobs. When we get to inflammation, I'll talk about the other jobs of glycine. But that's what we found, was that it extended lifespan anyway. Why? And we don't not sure exactly why it did in these mice. For example, it looks like the main reason it extended life was in slowing the growth of lung cancer, because most of them die of lung cancer. They die because the cancer grows and grows and grows, and finally it gets so big they can't breathe anymore, so they die. But glycine inhibits solid tumor growth. That's been demonstrated, certainly in animals. And that's how it increased lifespan there. But I believe that it generally will increase and certainly improve the quality, if not the quantity of life, because we know that it has a tremendous effect on decreasing inflammation. And everybody's dying one way or another from chronic inflammation. So glycine fights that in many ways, but that's how I got into it. And then realized, yes, glycine does increase longevity, or increase lifespan, or decrease whatever it is that's decreasing lifespan, so the animals live longer. But it wasn't doing methionine restriction. It was not affecting the amount of methionine. It was doing something else. And what it was doing was, it was basically, I think, doing everything else that glycine does, especially stopping chronic inflammation or inappropriate inflammation. But it had nothing to do with glycine and methylation. But that's how I got into it, into this particular corner of the biochemistry universe. Then I started taking it myself because, glycine's harmless, non-essential amino acid. You eat grams of it every day. So I sampled a little, like the old-time scientists. I'm old school, right? They used to do. So I said to our, people in the lab, you got a bottle of glycine? Yeah, here's the glycine. Fisher Scientific glycine. Open up the bottle and, don't do this at home. I mean, I do experiments on myself, and I don't necessarily advise everybody to do that. But everybody
medical advice.
themselves. It's just you got to know what you're doing. Anyway, so I tasted this glycine. It could have been a bottle of cyanide. I wouldn't do that, but it was glycine, and I tasted it and I realized it's sweet. That's why it's called glycine. Glycine means sweet amine. That's why I made a product. I call it sweet amine.
Yes.
That's what glycine means. It has a bad aftertaste, so you gotta kind of cut it with a couple other things, to make it taste more like sugar. But it's easy enough to do. You can cut it with sugar if you want. That's how I got into it. And so I did an experiment, and I started just taking 10 grams a day to see what would happen.
10 grams a day is way more than you're going to get usually from food. Or
From ordinary food, you get 2 or 3 grams. So I thought, let me take another 10, because if I took an extra gram or 2, I don't think I would notice a difference. But it seemed to me that this was something that would be important to do that with. It's like the scientific method is really, you have a question and then you get a hypothesis. Where'd you get your hypothesis? Rubbing 2 neurotransmitters together? Just...
Yeah.
You get struck by an idea, by a hypothesis in your mind. So, it's inspiration. Let's just call it inspiration. I was inspired to take 10 grams a day. And so I did that starting in 2008. And I didn't notice anything. I felt fine. Everything was good. No change. I kept taking it. What I did is I formulated like a Jell-O dessert kind of thing where I started with gelatin because gelatin has a lot of glycine in it. It's about 25% glycine by weight. So a 4-ounce serving of a gelatin dessert without any flavoring at all, or just with the juice flavoring, has half a gram of glycine in it. So I figured, okay, let me start with that. And I added another 8.5 grams per serving. When you make Jell-O, you heat up the water and you put in the gelatin, and then you dissolve the gelatin, and then you just add glycine. It's water soluble. And then you make your Jell-O, and that's how I had 10 grams a day. In fact, before I decided to go into business and sell it to anybody, I figured, well, I better make sure it's really safe. So I had 40 grams a day for a month, and I still felt fine. But I not only felt fine, but
Any additional benefit or just fine? You just didn't
I
notice
just
anything?
felt fine, but well, benefits retro. So, for example, when I say feeling fine, when I was, in my 30s and 40s and 50s, and it would snow, I was in the Northeast in upstate New York, and we would get snow just about every year, several times, and I would do shoveling. So I'd go out and I'd shovel the snow for snow blowing, but there are a lot of paths and pieces that you have to shovel by hand. So between the snowblower and hand shoveling, I'd be out there for an hour in a typical snowstorm, shoveling the snow, and then the next day my back would be sore. But I knew it would go away eventually. It was just sore for a day. So you say, but that was part of my feeling fine. Once I discovered the glycine miracle, as the book says,
Yeah.
and started taking 10 grams of glycine a day, I no longer had those pains. So now in my 60s, now in my 70s, but in my 60s and 70s, I go out and shovel snow for an hour, and I wouldn't even get sore. I felt better than I did when I was in my 30s. So it was helping there, but nothing I noticed because it was normal to me. And nothing seemed to change. But then a couple of things happened. I fell 4 feet onto a concrete floor directly onto my tailbone at the Home Depot one day. And although you'd think I'd have to go to the emergency room, I managed to get up and finish loading up the sheetrock I was buying and cutting. And that night, my wife and I had tickets to a dinner dance. We actually went dancing. And it
Crazy.
didn't bother me. And the next morning, I felt absolutely normal. Not even a pain in my rear end, nothing, where I had fallen. Just a huge bruise, as evidence that I had fallen, but there was no pain. Then the same year, I got a severe sunburn. And when I realized that I had this sunburn, because I was at a ball game, I wasn't at the beach, but it was full sun, it was near the solstice. There was a new stadium, no obstructions. And around the fifth inning, of this ball game, I started to feel a little warm on my thighs, and I looked down and I was like a boiled lobster. And I hadn't done this to myself since I was in my early 20s, certainly, back in my reckless youth, right? So I knew that I was going to be, and I was 100% certain, right? I'm going to have excruciating pain just dressing, undressing, bathing for the next couple of days. Life would be hell. But guess what? Once I got in the shade, it just started to fade. Went away. And then I realized, because I had done research on the skin in my graduate studies. I was with the dermatology department at NYU School of Medicine, and that's where I did my thesis work. So we do a lot of work on skin, so I knew about skin and inflammation in the skin and so forth. And, started to put two and two together and realized that this is inflammation, that between the fall, which should have created massive inflammation, and the sunburn, which should have created massive inflammation, I got zero inflammation because I was taking 10 grams a day of glycine. These are some of the most dramatic results I've ever had in any experiment I've ever done on myself or on any other lab equipment. I don't usually do experiments on animals, except these feeding things I was talking about. But I had never gotten such dramatic results in anything. That was, eureka moments, that it was really about inflammation. And then I started reading the literature more about glycine and inflammation. And there was an enormous amount of work, a great body of work that was done in University of North Carolina during the 1990s by a fellow named Ron Thurman, who was a toxicologist. And they did great work. Unfortunately, he actually died suddenly of a heart attack at the age of like 61, I think in 2001. And I think because even though he did this great work on glycine, he didn't try it on himself.
Do you know that for a fact?
If he had decided to try experimenting with 10 grams of glycine a day, he wouldn't have had a heart attack.
Do you know that for a fact that he didn't use glycine?
Yeah, I would say yes, because he had a heart attack. I would say that, as a doctor would say, I would say that's diagnostic for a heart attack. Is in order to have a heart attack, you probably need to be glycine deficient, unless there's some other really extraordinary event going on, like maybe, a skiing accident. You can get a fat embolism, which can get into your heart, stuff like that.
Okay, so can I say that's a very strong statement right there. That seems like a nice entry point because I've read in the literature higher levels of glycine potentially lower risk for cardiovascular disease. So tell us, what are the mechanisms?
Well, yes, and that may be, and also when I say in order to have a heart attack, I mean you have to be glycine deficient over the long haul.
Okay, yeah. So give us some context for that statement, and then talk about the various mechanisms. I know blood pressure,
yes,
platelets. I think glycine works on many different mechanisms.
Glycine works on many different levels.
Yeah.
As far as cardiovascular disease is concerned, the important level is that of inflammation. And when you think about the cardiovascular system, especially the arterial tree, that's a high pressure fluid system. It's like, when you turn on the sink or the tub or the shower, that's high pressure in those skinny little pipes that comes in to the basin. And a fat, slow moving water pipe is the drain pipe. So those are your veins. Your arteries supply that high pressure fluid, and the drain pipes, the veins, and also the lymphatic system are the drains that drain it out. So when you have high pressure fluids circulating like that, especially at branch points, especially at the highest pressure branch points, like where the carotids branch off from the brachiocephalic artery, from the systemic aorta, where especially where the coronaries break off or branch off from the coronary artery, that's virtually right there before they even get out of the heart, before they even get out of the sort of circumference of the heart, even though they're beyond the valve. That's where the coronaries branch off. So at that point where you have like a 90-degree branch point off a very high pressure fluid system, the highest it ever is in the body, you're going to get turbulence. And where you get turbulence, the engineers will understand this, wherever you get turbulence in a biological system like this, you're going to get damage. So just from, these stories about these wonderfully fit jogging people, and jogging is very good exercise, but did you notice how some of the key proponents of jogging, how did they meet their end? They died while they were jogging. Because if you have underlying cardiovascular disease, anything that's going to really make your blood pump harder, because your blood is hypercoagulable, may induce a clot. Well, the reason why your arteries become clogged up is because that injury is normal when you do exercise like that, and it's good for you, and it's normal to have minor micro injuries to your arteries, even your coronary arteries, all the time, because your body is designed to just repair them. No big deal. But if you're glycine deficient, you then get inflammation following from injury. See, nowadays, if you look up any source of information, whether it's WebMD or Wikipedia or any scientific journal or medical journal you like, you just look up inflammation and it tells you inflammation is the immune system's first response to infection or injury. And that's a half-truth. It is not a normal response to injury. That's what I found out with my self-experimentation. With severe injury, no inflammation. How's that happen? No infection. No need for the immune system to start secreting poisons to kill something that isn't there. So why does that always happen? Good question. It always happens because there is a nutritional deficiency that we don't recognize. And that's a deficiency in glycine. That's why it happens, because I know for a fact it doesn't happen. I had a very interesting conversation with a colleague about a year or two ago, and she was from your part of the country, like Colorado or someplace, nice, sunny, mountainous place. She had a nice tan, and I was talking to her about glycine and everything, about how I had that sunburn. And she says, "Oh, I don't have that problem." And I said, "Well, you have pretty fair skin." I said, are you like a bone broth fanatic?" She said, "Well, yeah, I am. I have bone broth every day." I said, "Oh, well, that's why. You're not glycine deficient. One of the very, very few." So she doesn't get sunburns. She, a little redness, but it goes away. And you might think, "Oh, that's my genetics. I don't burn, I tan, And there is a component to genetics, but I mean, with her, it was very clear. She gets enough glycine, and not many people do. If you take a glycine supplement, like Sweet Amine, I put in 8 grams, right? If you're ordinarily eating 2 or 3, that gives you the other 8. You get your 10 plus a day of glycine. You have enough so that your body does not do inflammation as a result of injury. Only infection, where it's appropriate and where it may save your life, because that's what it's for, but not in the case of injury. In the case of injury, inflammation only does more harm. In the case of chronic micro-injuries, like from blood circulation, heart attacks. In the case of chronic micro-injuries from ovulation in the ovaries, ovarian cancer. These have been epidemiologically demonstrated, that when you have repeated injuries or cases of massive cell death, what do you have? Breast cancer, what a scourge. Well, what happens every month when you're not pregnant in a non-conceptive cycle? The 3rd week of every cycle, your breasts grow because it's getting ready to feed a baby, if there is one, to come along in 9 months. Well, it starts to grow for about a week, and then when there is no conception taking place, what happens? The cells die off. The hormones disappear, the estrogen and progesterone that are making those cells multiply like crazy, they disappear. And so what happens? The cells die off. What happens when they die off? They get reabsorbed. No big deal, unless you're glycine deficient. Yes. So in most women, they can find that there is signs of inflammation in that third week, at the end of the third week of a cycle, when you're, the premenstrual time, PMTs, PMS, that premenstrual period, there's inflammation in the breast, low-grade inflammation. You might not feel any pain or swelling or anything. You might feel some pain and swelling in the early part of the menstrual cycle because that's when the breasts are growing. So you feel that breast tenderness, but you don't feel it in the third week of the cycle because that's when they are regressing. But there's a low-grade inflammation month after month, year after year. The more menstrual cycles you've had, the greater your risk of breast cancer. No surprise. Shouldn't be once you understand, the big picture of what's going on in the body with the hormones and the, all these physiological, whether there's exercise, injury, or micro injuries that happen due to physiologically normal events, even programmed events like ovulation and, menstrual cycle. All of these things in a glycine deficient body will chronically produce these conditions which give rise to things like cancer and heart disease. Now they're blaming everything on inflammation. Well, they're right. Why is another question, And it's not that these are the only things. Remember, I said we fed these mice glycine. They all died of cancer. Right. So it's not like, Britain says if I take glycine, I'll never get cancer, No. And remember, this is, first of all, I'm not a physician, so I'm not giving medical advice. I'm a scientist and a professor. Right. Emeritus anyway, but I don't give medical advice, number one. And number two, these things are not absolute. This is a nutrient. We all have finite lifespans on Earth. We're going to die of something, and it's going to be, and it used to be that cancer was one of the ways that old people died. You die of old age. One of the things, he died of old age. Well, what exactly did he die of? Oh, maybe he had lung cancer. Something like prostate cancer or lung cancer. Or I say prostate cancer because, they've done studies where if you do an autopsy on men who die, centenarians, everybody wants to know if you live to be over 100, what was the secret? So they've done studies where they do autopsies on centenarian men, and they find out that every one of them has prostate cancer. It just didn't grow, So cancer used to be one of the ways that old people would die. Now you get people in their 30s and 40s and 50s and even younger, they get cancer. Childhood cancer is another kettle of fish, but now cancer has become a bigger and bigger and bigger scourge, and we wonder why, because that should not happen to younger people, to middle-aged people. And one of the big reasons is diet. And you see what's happened with our diet, we get a triple whammy of glycine deficiency. Unlike our forebears, and I don't care what ethnicity you come from, your grandma did not throw the bones in the trash of whatever animal it was that she cut up for the for the meal. It went into the soup, not the trash. Because in the soup you actually, through boiling the bones, leach out the collagen, the gelatin. You'll notice you take the bone broth, you put it in the refrigerator, it gels. That's gelatin, and gelatin's 25% glycine by weight. So it's a lot of glycine. So we didn't used to throw that out. So now we throw it out. Now it's all, you get your fried chicken or you get your hamburger, or all of these things are muscle meats. So we talk about processed meats. Yes, processed meats are not great for you, but the worst processing is cutting the meat off the bone and throwing the bones away. That's the worst kind of meat processing that we do.
I love that.
So it's not the red meat so much that's killing you. It's the red meat not in balance with what it's normally attached to, the bones and the connective tissues that attach it, because that's all collagen. So that's one way that we're getting a lot less glycine. The other thing is, we're not only eating that meat, the muscle meat, more exclusively, but we're also eating more of it. It turns out when you eat more of it, what happens? Everybody's overweight. Not everybody. I was overweight. I lost about 25 pounds recently. It was an effort, but worth the effort. I had to because I was tripping into diabetes, and I will tell you about diabetes. I was in impaired glucose tolerance back in 2007. My mentor at the time, who I told you about, he was the one who was the dermatologist and syphilologist. We used to have a blood club. We used to draw each other's blood every week and look at so we had these longitudinal measurements of everything in our blood, and we'd do it first thing in the morning, before you'd eat, and so. My blood sugar came up 129, which is now considered diabetic. He says, I think you ought to maybe try and take metformin, And I said, I can regulate this with diet. I'll be okay. Don't worry about it. So what happened? That was 2007, and a couple of times it was bouncing 125, 127, 129, fasting glucose. Before that, it had been 95, 105, 110, 115, something like that. But then, that soon thereafter is when I started my experiments on glycine. So guess what? with glycine, I never went into diabetes. I stayed in impaired glucose tolerance until 2024. So it was about 16 years. For 15 years, keeping my glycine up high kept me out of diabetes and just in impaired glucose tolerance. So now I'm back in impaired glucose tolerance because I finally lost the weight. The study I like to quote is that diabetes can go away without losing the weight if you're glycine deficient to begin with. But that's another story. We're talking more about heart disease today, right? But anyway, just in terms of how you can be glycine deficient. So that's two ways then. If you're gaining more weight, which puts you in vulnerability to diabetes, more often than not you get diabetes if you're overweight. A lot of people are very overweight or obese. And what happens, a recent research from the Mayo Clinic in Minnesota, and also they have a branch in Jacksonville, Florida, and they have a children's hospital there. There was some very good research done in like 2023, 2024, where I love these doctors who are really good at doing research. A lot of scientists who want to be doctors and doctors who want to be scientists. I'm just a scientist, but this is a doctor who is a really good scientist. Some doctors are good scientists. Some are very good at both. His hypothesis was, we have a lot of children. It's a children's hospital, and most of the children in the hospital most of them are obese. A lot of them, 8, 10, 12, 14-year-olds, they're all obese. And so they have these medical problems, and they need to be hospitalized for this, that, and the other thing. So they did a study where they took a look at these obese kids versus normal kids, and they looked for markers of heart disease, the typical markers like CRP and other markers they were looking at. They looked at the whole metabolic profile to see what's different about these kids. Do they look like the same kind of blood profile that you find in older people, middle-aged and older people who have heart disease? They're too young to get the heart disease, but are they headed for heart disease? Can we tell by what the markers are in their blood? And guess what they found? Among other things, glycine. And they studied that a little further and found that there are several pathways to synthesize glycine, because they say it's not essential because your body can make it, but it can't make enough. One of the main pathways for synthesizing glycine, guess what, is inhibited in obesity. So your body is now making less glycine. So you eat all the muscle meats, and now you're eating too much food altogether. So eating all the muscle meats, that depletes glycine. You're eating too much food altogether, you get overweight, that depletes glycine. It's that way also. And then even the muscle meats that we're eating are depleted in collagen. Usually you have some collagen, like you have grass-fed beef. They have, their muscles are tougher, you need to cook them longer and so forth. Why? Because they have more collagen in them. So they're actually more nutritious. Anyway, there's a lot of things, at least 3 things that are going into being glycine deficient. It's the quality of the muscle meat, the fact that we're not eating the bones, and also the fact that our body is making less. That all contributes to making us glycine deficient. So obesity, and what I'd like to point this out with COVID, even though we're not talking about that, remember the comorbidities with COVID that made people die of COVID? If they had cancer, if they had heart disease, if they were obese, even if they weren't diabetic, if they were obese. They were all conditions in which people are deficient in glycine. There have been studies showing that those conditions, which are the comorbidities of COVID mortality, are also the comorbidities, also characterized by glycine deficiency. Yeah. So there's a lot of things, that way.
We're going to do an episode about that one next, but I want to bring you back for a second. So inflammation, right? I think everyone's waking up to the fact that if we just measure our serum cholesterol, it doesn't necessarily tell us as much as many people would believe. You have to look at the bigger picture, inflammatory conditions, right? Do you have elevated inflammation? But also we know that diabetes can be a precursor and increase the risk of heart disease. And we know that glycine, like you were saying, can keep you out of that diabetic territory. But there's also elevated homocysteine and elevated blood pressure and this antiplatelet aggregation impact of glycine.
Yeah, that's the other mechanism for keeping your coagulation down.
Can you talk about
however, I'm gonna push back a little bit because I'm not a fan of the idea of homocysteine toxicity. I'm not sure that that's really a thing. Because when that came out, first it was a research paper on genetic variant of people who had a deficiency in an enzyme called cystathionine synthase. Homocysteine combines with serine to make another amino acid called cystathionine. So it's cystathionine synthase is the first enzyme, and there are people who are deficient in cystathionine synthase, and so they had elevated homocysteine, and so they also were at higher risk of heart attacks. And so they said, oh, we can fix that. They gave him methylfolate and they lowered that homocysteine right back to normal. And the heart attack rate did not change. They still got the same rate of cardiovascular disease, even though they lowered the homocysteine to normal. So I still, unless I've seen something recently that's changed my mind, I haven't seen anything yet. It's not homocysteine that's the culprit. It really has to do with the methionine and glycine balance. If you have cystathionine synthase, it has to do with glutathione, for example. But there's even more about glutathione that I don't think it's quite everything that everyone thinks it's cracked up to be. It's important. It's an essential component. But glycine is one of those things that's so fundamental, that it's so important in so many pathways, that if you don't have enough of it, a lot of things can go wrong. However, your body knows that and makes enough of it to do almost everything it can with glycine. And the reason why it stops inflammation is because it is there almost like a salt. It does not have, in inflammation, its function is not biochemical. That's another thing that kind of throws the research off. It doesn't have a biochemical function. What it is a gatekeeper. It's a gatekeeper for channels that allow chloride ions to flow into the cell in order to balance it electrochemically, so that these immune cells, these macrophages, the first responders of the immune system, don't start shooting the place up with their poisons because they're activated, because they've lost their polarization, their electrical polarization at the surface membrane. So it allows these so-called glycine-gated chloride channels, otherwise known as glycine receptors. Glycine is the big hand that opens it up and holds it open. If it's not open, the glycine deteriorates, the voltage at the surface deteriorates, and the cell can be activated unnecessarily. So you get excessive reactions to infectious organisms. That's what the first series of papers by the Thurman group at UNC showed. They took these, I remember they took rat alveolar macrophages, the things that go crazy and cause the cytokine storm in COVID, alveolar macrophages, and showed them in the absence of glycine, or with very little glycine, you would see this tremendous electrical spike when the cell would get activated. When you put in lots of glycine, as much glycine as you could get when you supplement as much as you can, it did not prevent inflammation. It did not prevent the activation in the presence of bacteria, which tell it, yes, now it's time to get activated because these staphylococcus organisms don't belong here and we better kill them before they kill us. That's appropriate inflammation. And even with a lot of glycine, you get a nice sinusoidal spike. Very nice spike when you got a challenge with the bacterial lipopolysaccharide with a lot of glycine, but the spike was not crazy high. So you get an excessive reaction if you don't have enough glycine, or you get a reaction, you get these cells activated when they shouldn't be activated at all, as just with injury and no infectious agent present, no microbe. So that was all some of the wonderful research that was done in the 1990s by the Thurman group at UNC. So its role is in stopping inflammation, is doing just that. It's stopping the activation of the cell by holding those valves, if you will, those chloride channels at the surface of the cell open to allow the influx of this negatively charged chloride ion. And that's what keeps the cells normal and quiescent. Well, to do that, you need levels that are something in the neighborhood of north of 500 millimolar. Well, what does that mean? Well, you don't have to know much about it, except that's the way we measure glycine, is in millimolar units, micromolar units, which is a thousandth of millimolar. Micromolar units, how many micromoles per liter? Is that a lot? Well, that's actually a lot for amino acid. In fact, the normal range for glycine concentration, according to Quest Diagnostics or any of the other labs, is about 150 to 400, 350 to 400 micromolar. That's considered the normal range. So north of 500 is north of the normal range. But actually, if you're less than 500, you're glycine deficient. Because it has to be that high. Because again, glycine, for all of its biochemical uses, you don't need that much. There's plenty of glycine around, whether it's making cancer cells grow or normal cells grow or any other function. There's always going to be plenty of glycine around in a normal body, in a normally glycine deficient body. But for this purpose, for the stabilization of macrophages so that you don't get inflammation, you need a lot more there. So there are all kinds of things about glycine that have kind of thrown off ordinary research trends and trains of thought, including the fact that it's not non-essential after all. It really is essential, but not really for a biochemical function. It's essential for a cellular physiological function that has to do with the activation of the cells that cause inflammation. I had to pinch myself a few times years ago. When I first, made these discoveries, it was like, is this real? Could it be this simple? People to this day still tell me, it can't be that simple.
You're not presenting it as like the only factor. It is just a big
Right.
one.
Right.
It's
It's
factor.
not only that, but it is it's the critical factor. It is if you have chicken soup or bone broth, that's really what it is. If you could strip glycine out of bone broth, you're not going to get all those benefits of bone broth. So that is the factor, but that's a scientific principle called Occam's razor. It's the simplest explanation. That's another thing, doctors especially. You'll see that in my book, The Glycine Miracle. I point out a number of cases where doctors will do this wonderful research, and then they get into the discussion section where they discuss what the research means. And they'll talk about, the situation is it's complex. And when they say that, they usually mean they don't understand it. When you say that this situation or this process is complex, is usually a scientist's way of saying, I don't know anything about it. Saying, I don't know, and they're really kind of covering their rear ends, if you will. But it leads you to the wrong conclusions of saying, nah, it can't be that simple. But in fact, a truly scientific approach says, the simplest approach, this is Occam's razor, it's the simplest hypothesis that fits is usually the one that is acting. So you don't reject hypotheses because they're too simple, you reject hypotheses because they're too complex.
I love it.
Like, what is it? Ptolemy said all the planets and the sun revolved around the earth in these complex epicycles until, Copernicus blew them out of the water, and no, they just all go around the sun in simple elliptical orbits. There you had your simple explanation. The complex explanation was thrown out because it was unscientific. It had to be following the scientific method. It had to be discarded.
Yeah. And last thing before, because we're gonna tell people exactly how they can get enough, but I love this anti-platelet. I feel like this anti-platelet activation effect. So tell us about that, and then let's talk about
Yes. So platelets. Platelets, part of the clotting mechanism. There are a couple of different clotting mechanisms. One of them is platelets, which are these little plugs which plug up the holes physically. And then there are a lot of biochemicals that are involved, but some of them are made by platelets. So there's a couple of ways platelets are involved. So one of the ways that platelets are involved is that when platelets are activated, in order to do their thing, they get sticky. So one platelet sticks to another platelet, then they stick to the surface where the tissue is damaged, where there's a cut in the blood vessel, and they form a plug. So that's part of the clotting process. Well, they have glycine receptors, glycine-gated chloride channels. That was demonstrated by, again, the Thurman group. Showed that back in the 90s. Schemmer is the first article of that one. Anyway, Peter Schemmer. What happens is if you don't have enough glycine, your platelets are more sticky. And if you have enough glycine, they're not. So they will not form a clot abnormally. And we all know what happens when you have a clot that's abnormal. You can get an embolism. You can get a clot somewhere in the middle of a perfectly otherwise good vein or artery. It can get stuck in your lungs. You have a pulmonary embolism. Or if it gets stuck in your coronary arteries, you get a heart attack. If it gets stuck in your carotid arteries, you get a stroke. Dangerous things to happen when they're not supposed to happen. That's why it's a very complex series of interconnecting system to make a blood clot and also to make the blood unclot. Because when you have a clot form and all of a sudden that cascade of events which is necessary to amplify the biochemistry so that something that happens at a molecular level, a little cut, a little insult at a molecular level or a little bit bigger, can all of a sudden generate a clot that may be milligrams in size, can generate a fibrin plug that can plug things up. You need a lot of amplification. In order to amplify it, you need what's called an enzyme cascade. Enzyme A activates enzyme B activates enzyme C, and so on. You get about 7 steps till you finally get to thrombin, which takes fibrinogen and turns it into fibrin, which is the insoluble clotting material. Well, in order to do that, how are you going to do that without now making all of a sudden your whole circulatory system clot up? Because you have to have an unclotting cascade that's activated at the same time as the clotting cascade, which breaks up all the clots as they're forming before they are stabilized by an enzyme that sits where? Just outside the right where the breach is in the blood vessel. Right where the blood vessel is cut, you have your factor 13, fibrin stabilizing factor, which cross-links those fibrin fibers and makes that plug permanent, and instead of being broken up by plasmin, which is the unclotting enzyme. The activation of plasmin, the formation of plasmin, which breaks up a clot, is activated by another enzyme called plasminogen activator. And you may have heard of like tissue plasminogen activator, which was revolutionary to save people in heart attacks and strokes. And they still do it. That's the clot-busting enzyme, tissue plasminogen activator. So that stops the unclotting, so allows the blood to flow freely. That's how clotting happens, and platelets are less sticky to make their own clots, but platelets also make some soluble factors which participate in the blood clotting cascade, and one of them is PAI-1, PAI-1. That's called plasminogen activator inhibitor 1. If you, instead of plasminogen activator, there is also a plasminogen inhibitor, or what inhibits the plasminogen activator, which is more conducive to forming clots. So when you have inflammation, your platelets are more sticky, just even directly because they not enough glycine around, but you also have inflammation now, and the platelets are activated, so the platelets also secrete more PAI-1. So if you have more PAI-1, it inactivates the inhibitor of plasminogen and helps to stabilize clots, even where they shouldn't be. And then on top of that, you have inflammation also increases the liver synthesis of factor 7, which is one of the critical participants in that coagulation cascade of enzymes. So directly on the platelets and also indirectly through being inflammatory, when you are, people who have heart disease, people who have cancer, people who have blood that is in people who need blood thinners, right? Your doctor would know. He'll put you on a blood thinner, all right? People who need blood thinners have blood that is hypercoagulable, and glycine is your body's natural blood thinner. That's probably the easiest way to put it. And then people say, oh, can I just take glycine instead of Plavix? Well, once you're involved in medication, you got to trust the one who knows how to manipulate medication, because you're now beyond the normal parameters of what your body's used to doing, and you got to be supervised by a doctor. And I'm not a doctor anyway. Not only I'm not a doctor, I'm not that kind of doctor, and I'm not your doctor. So don't ask me about medical questions.
So not medical advice.
Right, I never give medical advice.
About that.
I will tell you how the process works that may be relevant to your condition. I will tell you what the research shows about it, and I'll tell you to ask your doctor if you want to know what you should do about it.
Yeah.
But, that's what I can do.
Yeah, that's perfect. And can you tell us, what is the state of the research here? Are there a lot of good trials looking at glycine supplementation and heart disease, either mortality, parameters?
Yes, There was some that was done by the Cleveland Clinic some years ago, where they were studying, because the Cleveland Clinic's a very big place, so they had hundreds of thousands of patients over the years, or millions of patients. So they had lots and lots and lots and lots of blood samples and genetic records and things like that. So they did a very interesting study where they had another one of these genetic variants, was a genetic variant for CPS, an enzyme called CPS. CPS is the first step in the urea cycle. So what is that? Well, urea is the way we excrete excess ammonia, most of it, that we get from amino acids. Amino acids have that amino part, that nitrogen, that ammonia nitrogen, and you have to get rid of it. So we can't excrete ammonia, you can't have it in high enough concentrations in your blood to excrete it without it being toxic. Ammonia is toxic, and it's a little bit of ammonia. That's another thing with nomenclature. They say ammonia, a toxin. Yeah, in the wrong concentrations, it's toxic. In low concentrations, it's normal. Remember I was talking about glycine being at least 500 micromolar? Ammonia, 5 or 6 micromolar, right? A lot less, 1/50th or 1/100th the amount of glycine you should have as ammonia, but you do have some ammonia. Well, in any case, most of the ammonia is converted to urea, and the first step of converting ammonia to urea is CPS, carbamoyl phosphate synthase. There's a genetic variant of that, and it was enough for the Cleveland Clinic to have enough samples to be able to look at disease, and they looked at MACE, major adverse cardiac events, among people with this CPS1 deficiency, because what is the a consequence of the CPS1 deficiency is, guess what? Glycine, as I said, it's like the most or the second most, I'm not sure which, abundant amino acid in the blood. You have a lot of it, even if you're deficient in it. So that's the major source of ammonia, which is the major source of urea. So if you get a backup in that pathway that makes urea, because your CPS1 is only half of what it should be because you have one bad gene for doing it, then guess what you're going to get a backup in? Glycine.
Yeah.
So they found that men, it wasn't true in women, probably because sex differences in the kidney function and in the expression of this function, but among the men who had CPS1 deficiency, the incidence of major adverse cardiac events was drastically reduced. But one of the most significant results I've ever seen, just tremendously reduced. It's like people who have CPS1 deficiency, men don't get heart attacks. It's like, they just don't. And so they wondered why, and they explored why, and they said, well, what is it about CPS1 deficiency? And they found out it was because glycine was high. And they did their other epidemiological adjustments. So you say, well, they have more glycine, but is it because of the glycine or is it something else? So they say, what if we adjust for this and what if we adjust for that? And they ended up, no, it's the glycine. Unfortunately, some of the subsequent work that this group at the Cleveland Clinic did, they didn't follow up on the glycine thing. After they had established in 2015 that low glycine was a risk factor for heart disease. This happens all the time. Discoveries are made and they don't follow up,
And what do they consider low glycine? And was there like a threshold, like with above a level that seemed protective? Like, you know what I mean? Like, was there a kind of like a glycine level?
I know you had requested some papers from me. Anyway, the first author of this paper is Hartiala, 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 2015, I think, and I can send you a copy of it.
Yeah.
But that was from the Cleveland Clinic, where they have a lot of patients in it. And as I say, they didn't follow up on what it was. What they didn't follow up was, what was it about the glycine that decreased the incidence of major adverse cardiac events? If they had found out, if they had just looked a little, that paper, that Schemmer paper from the Thurman group, that showed that glycine receptors are present in platelets and platelets respond, their aggregability responds to glycine concentration changes, they would have found that paper, because that paper was already in the literature. So the good work on the part of the Cleveland Clinic people, but not so good work on following it up and actually exploring the mechanism for why that genetic variant actually dramatically decreases the risk of major adverse cardiac events in men.
That's fascinating.
So I don't remember the details of the levels.
I have to buy it. So that's okay. That's okay if you don't remember. I'm just wondering what the goal is, though, and you've done a lot of research, that we get ourselves above that 500 micromolar.
Yeah, and people say, can we measure glycine? So I haven't measured my glycine levels. Remember I said we used to have a blood club. So in those days, my glycine was measured a lot. And I remember in the times that I was supplementing active with glycine, my level went up to about 720, 730, whereas ordinarily it was down to like 300 something.
And I'll have to test mine someday, because I had the same thing as you. Like, I actually just realized I fell the other day, and it didn't like bother me, and I didn't wake up, but when I saw the bruise, I was like, whoa! But like, it didn't stop me in my everyday life, because there isn't a lot of pain. I had to see it visually, and so I need to test them one day, and we're going to talk right now about how you get enough, and like he's been hinting at, bone broth daily. I do 2 to 3 cups, gelatin daily, collagenous cuts, grass-fed meats, connective tissue. Now, I eat glycine, but Dr. Brind has also formulated something. So tell us about sweet amine, but also, why is sweet amine different? I've been getting questions. Why is sweet amine different than any other glycine supplement on the market?
Well, the only thing that's materially different is that it has taurine in it. I also add a little less than a gram of taurine, 800 milligrams of taurine in it. Otherwise,
it's more designed to be added to food, right? And like you make your like glycine lemonade in the morning, where you put like a lemon and water and sweet amine. So it's less like I gotta take it. It's more like something you can enjoy.
It's food, I mean, it's not. It's food. It's not medicine. It's not made to give you some superhero amount of glycine in your blood. It's made to give you a healthy amount, which most people just don't have. But otherwise, the main thing is it's just taste. I mean, I tweak it a little bit with natural sweeteners to make it a little bit more like sugar, but it really has almost no calories. It's got like 24 calories, and the main thing is that It's convenient and portable, so you can carry it with you on the plane. You can take a box of it with you and pack it in your carry-ons. They'll open your carry-on to see what you got, if you got 10 or 12 boxes in there, as I sometimes do, and then they'll test it and say, oh, it's okay. But it's portability and convenience. And some people say, oh, I can buy glycine a lot less cheaper, just buy glycine powder. And I say, yes, you can. Because whenever you formulate anything into a prepared product, even a capsule as opposed to a pill, even a capsule or a packet of anything, half the cost or more is in the packaging. So, you can, you want to, if you don't want to, if you can't afford it, and most of my customers pay because I run sales and they buy like months' supplies at a time, several months at a time. Most of my customers pay about or less than $1 a day, and that's not a whole lot. You say, oh, I can get all the glycine I need and buy it in bulk and do it for 25 cents a day. Yes, you can. You can also go to Starbucks or Dunkin' Donuts and buy your coffee. You can make it for 1/10 the price in your own kitchen.
Yeah.
Yeah. It's a matter of taste and convenience and all of that. And the point is, many times or a few times more expensive than buying bulk glycine powder, but it's still very, very cheap because many times a very low number is still a very low number. So for less than $1 a day, or about $1 a day, give or take, depending on how much you buy at a time, it's not, it's really a convenience. So and if you don't have to use my suite. I mean, you can buy glycine from anybody else. If you want to get just glycine, if you want to get just organic stuff because it's for bone broth, then
and you can make your own bone
broth. Get your glycine one way or another. Just get it. I don't care who you buy.
Yeah, that's exactly right. We're just here to raise awareness around the deficiency of glycine and how it links to the other conditions. And like you said, we're not just trying to sell you. So make your own bone broth at home. That's probably the cheapest way if you have the time and the desire.
If you're paying nothing for the bones, yeah, but
if you're paying nothing for the bone, yeah, and
bones are expensive though.
They can be expensive. Yeah, that is true. So yeah, we've given you so many different options. Thank you, Dr. Bryn, for your passion and your research, and for spending time with me again. I thoroughly enjoyed our conversations, and
love to talk about
this. Let us know about your comments.
That's because I'm an emeritus professor, so I don't have a classroom every day to talk in front of. So I'm, I got to get my fix.
Well, we are very excited to be your classroom, and let us know if you guys have any topics or questions for us to delve into in future episodes. And thank you so much.